Hello everyone, my name is Daniel Fuentes Ibarra and I am a postdoc at the University of Texas at Austin. Today I'll be presenting a poster on a characterization framework for high pressure CO2 nanobubbles. To give a little background, nanobubbles are cavities smaller than 200 nanometers. Because of their extremely small size, they exhibit very high internal pressure and long-term stability. Recently, nanobubbles have gained a lot of attention in areas like enhanced oil recovery and carbon storage. For instance, it has been shown that nanobubble displacements can improve oil recovery by about 16% compared to conventional water injection, highlighting their strong potential for subsurface applications. One key reason is that CO2 nanobubbles can hold up to 1.5 to 1.8 times more CO2 than inherent solubility of water due to supersaturation and capillary effects. However, despite these promising results, the thermodynamics of nanobubble remain poorly understood, especially under high pressure conditions relevant to reservoirs. So, the goal of this work is to develop a characterization framework for CO2 nanobubbles at high pressure and ambient temperatures. To achieve this, we combined experiments including nanobubble generation, gas content measurements, and size distribution from dynamic light scattering, along with thermodynamic modeling using the GERD 2008 EOS, which accounts for supersaturation and capillary pressure effects, formulated with Helmholtz energy minimization, allowing us to calibrate the EOS against experimental pressures. This integration enabled us to quantify key nanobubble properties such as capillary pressure, the fraction of gas in bubbles and dissolved, bubble number density, and the degree of supersaturation, among properties. These outputs provide valuable insights for developing predictive models of CO2 nanobubbles in subsurface applications. The first step in this framework is to generate the nanobubbles by co-injecting CO2 and carbonated water through a porous membrane in a core holder, and then collecting the sample in a Safari cell. To measure gas content, the Safari cell is connected to an accumulator with a piston set at the top. The sample is gradually depressurized and then collected water corresponds to the amount of CO2 from the nanobubble fluid. Then the remaining water in the cell is also collected, and together these measurements allow us to calculate the gas content. For bubble size, DLS measurements reveal a bimodal distribution of diameters. Once we obtain the gas content and the radius of bubbles, we can use them as inputs for the thermodynamic model. The model solves NC fugacity equations plus one equation for capillary pressure, formulated with Helmholtz free energy minimization. At equilibrium, the differential of Helmholtz free energy approaches to zero, while capillary pressure follows the Young-Laplace equation. From this modeling, we obtain outputs such as capillary pressure, the percent of bubble dispersion, bubble number density, among other properties. In the table at the top, we present nanobubble measurements at three different pressures: 1200, 1700, and 2250 psig, corresponding to supersaturation ratios of 1.66, 1.54, and 1.82. The DLS data shows a bimodal bubble size distribution. Before proceeding to use the EOS model, we first calibrated its parameters with inherent solubility data. Then, For each nanobubble fluid, we assume a unimodal distribution for individual subsystems at equilibrium. After adjusting the external pressure, we obtain the properties for each case, including percent of CO2 in bubbles, number density, and capillary pressure. Overall, results show clearly that the capillary pressure, number density, and gas content increases with pressure, while bubble radius decreases with pressure. So this is all on my end. I would like to thank my supervisor, Dr. Kuno, as well as our collaborators and sponsor for this for their support in this project.